Okay, folks, good afternoon. I would like to remind you guys that we have a quiz on next week on Tuesday. The topic is going to be multi-level power electronic converters. Also, about an hour ago, I posted the solution to homework number 5, I believe. I think it was homework number 5 or 4. It's quite simple. Take a look. If you have questions, let me know. So basically, we had a buck-boost converter. You had to identify the single-pole double-through switch in that buck-boost and then replace it with a current mode controlled cell. And then you could write a KCL on the left-hand side to basically find F1 and G1 and R1, and then write a KCL on the right-hand side to find F2, G2, and R2, and then find the transfer functions. And all of our transfer functions are first-order transfer functions. As far as the multi-level converters are concerned, now that we are familiar with the topic, we may want to actually go back and basically see what we were talking about at the very beginning. One application for these converters is when you're dealing with higher voltages that are higher than the tolerance of one individual switch. So you can actually, for instance, process 1200 volts, whereas the IGBTs that you have are only 600 volts. So likely each IGBT or each transistor in general is shouldering part of the voltage, part of the load. The other one is, the other advantage or basically motivation for us to go ahead and use these converters is low harmonics. A lot of times, ideally, when you're dealing with, for instance, the power grid or an electric motor, the voltage that you're supplying to the system should be as close as possible to an AC signal and a sinusoidal AC signal. And as we saw, multi-level converters have a better resolution when it comes to steps of the voltage. They are modular, so that could be an advantage in terms of the cost of manufacturing them, and also because the voltage on the switches are lower, therefore dV over dt is also lower. The first category that we discussed was cascaded H-bridge converters. We have one H-bridge on the screen on the left, which can give us three levels of VDC, 0, and negative VDC. And obviously, if you have a bunch of them placed in series with each other, then you can actually increase your levels. The problem with cascaded H-bridge converters is each H-bridge needs an independent source, DC source. Sources are floated. They don't have a common ground. But there are papers out there that are actually suggesting that we need to have only one main source and the remaining of the H-bridges could be fed by a capacitor. And then you have to regulate the voltage of the capacitors and stuff like that. The second category that we discussed was diode-clamped multi-level converters. So the idea was how to build a single pole, for instance, the triple throw or quadruple throw or even more throws or M throws in general or N throws using the semiconductor devices that we have. For instance, what we have over here is the switch realization for a single pole triple throw switch, and the current is bidirectional. It can actually accommodate positive and negative electric currents. The good thing about these converters is it's easier. You don't need as many independent sources of DC. Even though our first examples we had DC1 and DC2, then we moved on to the cases that if there is a certain amount of symmetry in the system and your electric current is sometimes symmetrically positive and sometimes symmetrically negative, you can argue that as long as basically this IX current is 0 on average, you can eliminate the need for having two independent sources and just use one main source that you have and then split it into two using two relatively large capacitors. So we looked at this one as well. Also, we extended the idea to even more number of levels. For instance, what I have here can accommodate actually 4 levels of 0, VDC over, or V in over 3, 2 V in over 3, and V in. So basically, your steps are always less than V in. Again, here you're using 3 capacitors to kind of manipulate these levels. Now, the good thing about these converters is if you're using them in a 3-phase configuration, you can actually use these 3 capacitors for all your 3 phases. You don't need 9 capacitors. You only need 3 capacitors for 3 phases. So that's actually an advantage. Although you can argue that, again, there are papers out there that they argue that you can naturally balance the voltage of these capacitors if there's a certain amount of symmetry in the system. And there are papers discussing that what if there is not enough symmetry in the system and, for instance, the voltage of the caps are not equally divided or shared, so then you need to have an active method of equalizing the voltage of these capacitors, meaning that actively you should be able to control the average value of this current or this electric current. First off, whatever you want to control, you have to measure. So measuring this capacity, the voltage of these capacitors might be challenging because we are talking about high voltage applications. And the other thing is you don't have all the same ground. So basically, if the ground in the system is down here, measuring the voltage of this cap is easy, but the one in the middle is actually kind of floating with respect to that ground. So that becomes a little bit challenging. So you have to basically spend some time, come up with a good voltage sensing, approach, or buy a fancy sensor, basically.
Excuse me.
Yes.
Is having different voltage of capacitor is not an advantage because lesser number of redundant levels would be having?
That is right. I mean, you can argue that under certain scenarios, the voltage of these capacitors do not necessarily have to be equal with each other. But at the same time, you can argue that the most common practice, to make it simple as it is, make sure all of them are equal. And you pretty much, in terms of number of levels, you can achieve a good accuracy and a good resolution. So you don't really have to go after, the voltage of this capacitor is 2.5 times the other one or something like that. The most common, I would say 99.9% of the papers that I've seen, they always assume the capacitors are equally, the voltage of the capacitors are equal, basically. But yeah, you may come up with a very crazy approach that, let's at least temporarily double it or half it or do something like that. Any other questions? Okay. We also talked about once the configuration gets a little bit confusing, once we have so many switches and so many diodes, you have to be able to identify which switch and diode pairs are actually complementing each other, making a single pole double throw switch. We kind of branched out a little bit. We said, okay, we have H-bridges. Now that we know how to build a single pole triple throw switch, we can combine that with the H-bridge idea and even achieve more number of levels, and we looked at some redundancy. And the last category in multi-level converters that we discussed was flying capacitors, and we are going to see why they are called flying capacitors, or they're called capacitor clamp. Instead of diode clamp, they are called capacitor clamp multi-level converters. The basic idea comes from the fact that basically this very simple cell structure. And I kind of broke down my single pole double throw switch to 2 single pole single throw switches, which are S1 and S1 prime. Obviously, they are complementing each other, so I didn't label them S1 and S2. I just labeled them S1 and S1 prime. And I kind of extended to the left-hand side to actually add more sources. Switch realization is very easy. It's just one, for instance, IGBT or a MOSFET with the anti-parallel diode. As long as the voltage that you have on the left, the source on the left is larger than the source on the right, you're good with this switch realization, and it can handle bidirectional flow of the electric current as well. So we looked at a very simple case of only having 4 switches and 2 sources of DC sources, VDC1 and VDC2, or n equal to 2, number of stages equals 2. And we looked at different possibilities. There are 4 possibilities because we have 2 independent switches, and we can basically synthesize VDC2, which is a larger voltage, or the difference between VDC2 and VDC1, which is still positive because VDC2 is larger than VDC1, or we can make or synthesize VDC1 and 0. So basically we can achieve a total of 4 levels. However, the most common practice is to basically assume that VDC2 is twice as much of VDC1. In that case, we can only achieve 3 levels. 2 of the levels are giving us identical voltages. One of them is VDC2 minus VDC1, which is again VDC1, and the other one is VDC1 itself. So you can argue that in one of these modes, source number 1, which is not a capacitor yet, but soon it is going to be replaced with a capacitor, can be charged, and in the other case, it could be discharged, assuming that IOD is positive. Then if IOD is negative, you can make a similar argument. So you can argue that even though you don't even need a lot of symmetry in the system, even when IOD is always positive, for instance, you are using this topology in a DC to DC converter kind of a thing, you can argue that it is possible to make sure that on average, source number 1 is neither providing or absorbing any power or energy, or if you replace it with a capacitor, you can regulate the voltage of a capacitor at a particular point and not being worried about this capacitor on average is going to get charged or discharged. So you can actually regulate the voltage of the capacitor at your desired level, which is half of your main DC source. All right. Any questions so far? Yes.
What does the dash mean? Like, if it is not
this dash over here, you mean?
Source 2, yeah.
This one?
Yeah.
That means nothing is happening to source number 2.
Okay.
Source number 2 is not connected or engaged. It's open, basically. Okay. So technically, this topology could be used. So basically, this is okay. So I'm going to write it over here. Same story. So the conclusion is, regardless of the polarity of the output current, you can always find possibilities or opportunities to charge or discharge source number 1, as long as basically VDC1 and VDC1 is half of VDC2. So then the conclusion would be by a capacitor. Okay? Which is good. So technically you would like to have only one major DC source, and the rest of the components, the rest of the sources are kind of fake sources, which are actually capacitors. So technically, if I want to draw a block diagram here, let me call it flying capacitor. With the number of stages being 2, so you have VDC, which is your main source of energy and power, and then you have VC. Okay, and then you have an output voltage, which could be at 3 levels of 0, VDC over 2, and VDC itself. Okay, and then we are trying to, as I said, we are trying to regulate the voltage of the capacitor at half of VDC. So technically you need to have a kind of a feedback loop to make sure that happens. So that feedback loop is here. So you're measuring your output voltage. And obviously you have a reference for your output voltage. We are not going to discuss where this reference comes from. It could be a staircase kind of a waveform, or it could be a sinusoidal waveform, or whatever it is. At the same time, this controller needs to know what the value of this capacitor voltage is, and then make a bunch of decision in terms of which state needs to be chosen. And the logic of this controller is if your desired output voltage level is VDC over 2, so remember this V out is something like this, for instance. Okay, something like this. Or there might be a PWM also in it. So if your desired output voltage is VDC over 2, for instance, you were trying to synthesize or make a level like that, you have two options. You have to look at your output current, for instance. Which also says that, technically we are measuring, this is measuring the output current basically. This was not measuring the output voltage. If your desired output voltage is supposed to be VDC over 2 and the output current is positive, and also let's say you're measuring this capacitor voltage as well, and the capacitor voltage is more than where it is supposed to be, more than its reference, basically then choose a state number 3. And a state number 3 comes from this table from above. This is a state number 3. So the whole idea is the capacitor has to be discharged because the voltage of the cap is slightly higher than where it is supposed to be. And this argument was valid for I out being positive, so we have to look at the polarity of the output current as well. And the other logic is if you happen to find yourself in a situation that your output voltage level should be VDC over 2, and still the output current is positive, but your capacitor is the voltage of the cap is slightly lower than where it is supposed to be, then choose state number 2, because the state number 2 is actually charging the capacitor. Okay, so something like, so it's a very simple logic, and this logic that I wrote is only for the case when your I out is positive. In some applications, I out is always positive. For instance, a DC-DC conversion, unidirectional DC-DC conversion. If I out changes its polarity, then you have to write two other lines for those basically cases that I out is negative. Okay, question.
If we implement this practically,
Mm-hmm.
if we see we are comparing the capacitor voltage with the reference VDC by 2,
Uh-huh.
and again greater than and less than. So practically we have a certain ripple voltage, right?
Right.
It may oscillate like sometimes greater, less, greater, less.
That's a good point. So there are ways of avoiding that. For instance, one simple way is instead of continuously looking at your capacitor voltage, take samples of your capacitor voltage, like every, 10 milliseconds or something like that. So take a sample of capacitor voltage, then look at it and analyze it and apply your new switching state, and then wait a little bit longer and then take the next sample. So that's one way of doing that. Or you can, for instance, put a low-pass filter. After you have measured your capacitor voltage, you can place a low-pass filter that having like a moving average that is telling you where the capacitor voltage. Instead of looking at the instantaneous value of the cap voltage, look at the history of the capacitor voltage. And that way you are kind of immunizing your system against some measurement noise as well. Good question. Other questions? Okay. So this is all about flying capacitor converters. I'm going to draw another one over here. This one actually has more capacitors. So by now you should know why they are called flying capacitors, because we use a lot of capacitors in them, and the capacitors are kind of floated. They don't have common ground. They're kind of in the middle of the system. So the way they are usually presented in the literature, they look nothing like what I drew over here. They look what I am about to draw actually on the screen. So this one that I'm about to draw has 3 capacitors and the main basically source. So we are using 4 IGBTs on top and 4 IGBTs in the bottom. So these 4 transistors, assume that n is equal to 1 or number of 4, or its number of stages is 4. These transistors are S1, S2, S3, and S4 basically. Then we have S1 prime, S2 prime, S3 prime, and S4 prime, which appear down here. Oops. Now, generally speaking, our current could be -2, so we may want to add these diodes here as well. So we are using 8 transistors and 8 diodes. Oh, by the way, before I get here, let me also mention, when I was talking about this control logic, in some applications, again, there is certain amount of symmetry in the system, like I out is symmetrically positive and negative. It's like a sinusoidal current. You don't need to actively regulate the capacitor voltage. It's called natural balancing. Your capacitor voltage will naturally settle at VDC/2, okay? So if there is certain symmetry in the system, you don't really even have to add this control loop to the system. Okay, so let's go back here. All right, so my first capacitor sits here. Second capacitor sits here. Third one, and finally your main source. Okay, let me just see if I can, okay. Okay, so this is your topology. So I'm going to label this to be S1 and S1 prime. These 2 switches complement each other. Then S2 and S2 prime, S3 and S3 prime, S4 and S4 prime. Okay. I'm going to label these capacitors C1, C2, C3 and VDC. Okay. Now, we had a little bit of a discussion about this before. It depends on where you assume your ground is. If you want to have like a unipolar output voltage, for instance, this is a three-phase system, you can argue that this is our ground and my output voltage is measured from here to here. But at the same time, if you are trying to have a bipolar output voltage, you have to split your source using two capacitors, or maybe you have two kind of half sources placed in series with each other. So then you have to put your ground. For instance, if you have a second source here too, you have to put your ground over here, something like that. So keep that in mind. But over here, I'm just going to make things simple and assume that I'm looking at a unipolar output voltage, and this is our output voltage basically. Okay. Now, when we had only two capacitors, when we had only two stages, one of them was a capacitor, and the voltage of that capacitor was at the half of the source. Here, since we have three of them, this is how you basically distribute the voltage between them. So usually we call this voltage to be E. And this is going to be, and then this is going to be twice E, and then 3 times E, and this is 4 times E. Okay, so the capacitors are the most inner one, has the smallest voltage, then the one on the left is twice that, and then the second one is 3 times that, and all the way up to the source. So I'm going to write these up here as well. So my VDC is 4 times the first capacitor, the voltage of the first capacitor, which is 4E. And then voltage of the capacitor number 3 is 3 times the voltage of the capacitor number 1, and so on and so forth. Okay. Okay. So we can argue that using this particular voltage selection, first of all, there is plenty of opportunities to charge and discharge these capacitors. We have a lot of redundant states, and ideally we should have 16 states because we have 4 independent switches, so 2 times 2 times 2 times 2 is 16. But using this selection of voltages, we can actually achieve only 5 levels with a lot of redundancy. So total stiff voltages is how about total number of okay, so as I said earlier, stages, so that means technically we have 4 kind of stiff voltages. 3 of them are capacitors, 1 of them is our main source. So number of levels would be basically n plus 1, assuming that this selection of voltages has been made. Okay, but if we were going with a very general case of instead of all these capacitors, I really had independent sources of voltages of VDC1, VDC2, VDC3, and VDC4, then I should have had 2 to the power of n basically voltage levels. So in general, if we're independent, independent, I mean that I couldn't write a linear relationship between one voltage, two other voltages to achieve the third one. Like here I can say the voltage of this cap is this one plus this one, basically. If I couldn't do that, I could say they are independent of each other. Then the number of levels would be two to the power of n, because we have n independent switches. Each switch has two states, so 2 times all the way to the n. Okay, so this is a 5-level, basically, flying capacitor, multi-level converters. Although in a bipolar application, some people only count the 0 and positive levels. So our number of levels all of a sudden reduces down to 3, meaning that we have 0 and 2 positive levels and 2 negative levels. So some papers do it like that, but usually it's not a bad idea to count all the levels, which is 5. Now I'm going to have a table down here kind of explaining what is going on in this network in terms of switching pattern. So let's say we are kind of having like a lookup table that relates the switches on and off states with the output voltage that is generated. So if I keep all of these switches on, this one is on, S2 is on, S3 is on, and S4 is on, this is going to be 4 times E. So why is that? So technically what I'm doing is I'm turning this on. So as you can see, my output voltage is all the way appearing on the output. My input voltage is all the way appearing on the output side. And the input voltage was 4 times E. So V out is 4 times E. All right. Now let's consider another case. I'm doing a binary thing over here, by the way. So this is, for instance, 1, 1, 1, 0. I will get 3E. All right, now let's take a look at this one. So S1 is off, but S2, S3, and S4 are on. All right, let's go up here. S2, 3, and 4 are on. And S1 is off, meaning that S1 prime is on. Okay, so this is going to be our conduction path. So as you can see, it's like we already have VDC, and then we have put the first capacitor, flipped it, and put it on top of VDC. So we have VDC minus VC1, which is 4E minus E, which is 3E. And by the way, in this case, if I out is positive, for instance, capacitor number 1 is going to get charged. So that's where this 3E comes from. So let me erase this. Okay. Now, another possibility, we have basically 4 stages that would generate 3E, 4 redundant states, basically. Another one could be this one, 0, 1, 1, 1. This would give us 3 as well. And why is that? So S1 is on, S2 is on, and S3 is on. So let's take a look. These 3 guys are on. And then S4 is off, meaning that S4 prime is on. So now if you see, basically what we are doing is we are taking capacitor number 3 and shorting it to the output side, basically. So the output voltage is the voltage of the third capacitor, which is 3 times E. All right, so let's get to the other states. For instance, 1, 0, 1, 1. This would give us 3 as well. All right, let's take a look at this one. So S1 and 2 are on, S3 is off, S4 is on. So on here, and S3 prime is also on. Okay, so we start from here, we go here. So this is how the current would flow. Would come down here, would flow over here, would come down here, oops. So something like this. So it's like we are kind of flipping some of these capacitors, like technically my output voltage is this voltage, which is 4E, minus this voltage, which gives me just E, plus this voltage, which gives me 3 again, okay? And in this case, you can argue that this capacitor, assuming the output current is positive, this cap is getting charged, and this cap is getting discharged. So in all of these redundant states are going to come in handy when you're trying to regulate the voltage of these capacitors. As I said, there's a natural way of doing that, and let's say you don't want to do the natural way. All right, so the following stages, I'm not going to just go through that. I'm just going to basically write it over here. You guys can, can verify them. Yes.
Can you explain the stage where S4 prime is on?
Why S4?
No. I mean S3, S2, and S1 are on, and S4 prime is on.
This one?
How is the voltage?
This one?
Yeah.
S1, 2, and 3 are on, and S4 is off, right?
Yeah.
Okay, so let's take a look. Okay, 1, 2, and 3 are on, and S4 is off, meaning that S4 prime is on. So from here to here, you only have this one, right? So only capacitor series C3 is engaged. There are other ST voltages are not engaged, basically.
But at S3, top node VDC is again available, and so it basically.
Oh, VDC. Oh, but the thing is, you mean at this node?
Yeah, S4 is open, so.
S4 is open, so it's off. So basically, VDC is kind of open. Okay. So VDC is connected to here. Yeah, VDC is connected to this end, but is not connected from the top side. All right, let me erase this. Okay. So these are the 4 possible scenarios that we can synthesize 3E. And there are 6 possible scenarios to synthesize 2E. So I'm just going to write them over here, like 1100, 0011, 1001, 1010. I think I'm missing one. Okay, 1100, 0011, 1001, 01. Okay, it doesn't really matter. I'm just gonna want to be consistent with my notes. 0110, 1010, and finally 0101. Okay, and there are 4 possibilities to synthesize E, which is 1000, 0100, 0010, and 0001. And finally, there's only one possibility to synthesize 0, which is our last level, which is if I keep all of the top switches open, and therefore all of the bottom switches are closed. Okay, my output is shorted to the ground, basically. All right. So you have this table. This table is very easy to be programmed in a DSP. It's just a very simple lookup table. As you were seeing, to synthesize a particular output voltage, we have so many options. So we can, for instance, look at which option provides least, switches to be engaged, to be on, because conduction losses of the switches is important. The other one is in some of these states, for instance, C1 is getting charged. In some of them, C1 is getting discharged. Then selection of that state would become important depending on where the voltage of the capacitor is. A few years ago, we had a paper on this, or maybe several papers on this, kind of going through this logic of selecting the capacitors, and which one of these redundant states you better choose to, for instance, minimize the losses or achieve a faster voltage regulation or something like this. One thing to note is, if you see, for instance, number 3 appears here, and I have 3 switches on. So whenever I want to, so a general rule of thumb is, if you want 3 times E to appear as your output voltage, pick 3 of the switches and turn them on, and one of them is supposed to be off, and that's going to happen. Also, if you want to generate 2E, pick 2 of the switches and turn them on. See, all of these have 2 switches on. 2 here, 2 here, 2 here, 2 here. So all of these guys would give you 2 times E. You can prove it. All right, any questions? Yes?
So once we select a level, the only algorithm that we are putting in the controller is for the charge balancing of capacitors?
That's right.
Okay.
So yeah, so presume that your desired output voltage is a staircase output voltage. For instance, your Vout is supposed to look like this. 1, 2, 3, 4.
It's not a fixed output voltage.
Okay, so your output voltage is kind of a staircase output voltage, and I'm just giving you one simple case of a single phase kind of a thing. If you have 3 of these, then you can look at line-to-line voltages, and your ideal scenario is you are trying to create a sinusoidal line-to-line voltage, basically. Trying to emulate it like this. So technically, you're trying to emulate this to look like a sinusoidal signal. Okay? Something like this. So, for instance, you are at this point, and you're trying to generate 2 times E. Oh, come on. Let me do it again. Okay? So, in terms of time, you are here. So you're trying to synthesize 2 times E, and then you have 6 options. Which one of them are you going to choose? It depends on which capacitors are charged, which capacitors are undercharged, and which state achieves the goal that you want, that all of the capacitors should be regulated at their desired value of E or 2E or 3E, something like that.
So the switching is fast enough that before the output voltage actually changes, the charges are balanced out.
Oh, yeah. So the switching, okay, you should say the capacitors are long enough that once you select a state, even though the output current is flowing through these capacitors, they don't drastically get discharged. So for instance, from 500 volts, they come to 495, something like that. And again, remember, this is just a simple demonstration because practically you might be doing PWM. All right, something like this. So again, your conduction window for a capacitor might be very, very small.
So each PWM cycle, you could choose a different mode
Exactly.
of operation.
So yeah, exactly. So there you have a DSP that you know where you want to be in terms of your output voltage. Which one should I choose? And then you have to look at the capacitor voltages and choose, oh, this is going to give me the best regulation possible, something like that. So if you're interested to learn more, let me know. There's at least one paper. I know we have published it, but I'm sure there are more papers out there describing this. Yes?
You talked about the step voltages
Mm-hmm.
when it's like number of level, like 2 to the power n.
Uh-huh.
When it's independent. step.
Right.
Like for example, I didn't understand this one.
Okay, so if you select your capacitors to be E, 2 times E, 3 times E, and 4 times E, that means there's a relationship between these capacitor voltages.
This is different.
You only get N levels. I'm sorry, N plus 1 levels. If you randomly choose them, for instance, choose them 120, 175 volts, 216 volts, and something else, for instance. So they're totally not related to each other at all. You can generate up to 2 to the power of N levels. Now, some of those levels are tiny, some of them are far, but theoretically you can go all the way up to 2 to the power of N levels of voltages.
Excuse me. As we have a lot of redundant levels, is there any possibility like we can replace a transistor with just a diode?
Unfortunately not. Excellent question. Redundancy over here does not help us simplify switch realization. Your switch realization is as it is. You cannot really further simplify it. Although you can argue that, switch realization over here is also dependent on the polarity of your output current. If your output current, for instance, is always positive, first of all, the question is, if your output current is positive, why in the world you want to have an output voltage like this? So let's say we don't want to address that question, which is a silly thing, but presumably if your output current is always positive, you can argue that on the top over here, I only need the transistors, not the diodes. In the bottom, I only need the diodes, not the transistors. Okay? So if your output current is always positive, but the question is, do we even have an application that we want to synthesize a crazy looking output voltage like this, which is almost AC, but our current is always positive, which is never going to happen. However, I have an example for using this topology in a DC to DC conversion. So over there, you can argue that your switch realization would be easier. Very good question. Other questions?
The capacitor size, do we have a trade-off between the PWM and how big the capacitor?
What was that? What was the first part?
Capacitor, how big the capacitor is.
Oh, how large the capacitors are supposed to be in terms of size. Well, I cannot give you a magic number, but for instance, what you can do is you can run the simulation, and the capacitor size is dependent on the amount of current that passes through the capacitor and the duration of time that current passes, basically delta Q, basically, okay? Current times time, which is delta Q. And you want the capacitor to be large enough that if certain amount of delta Q is added or getting taken out of the capacitor, the voltage of the capacitor doesn't change much, okay? So remember, once you find delta Q, again, that's depending on the application, your power level. Let's say you have run some simulation. And remember, delta Q is, I'm sorry. All right. And you have determined your worst delta Q, like for the maximum amount of power, this amount of delta Q is coming out, and it depends on your switching scheme as well. Then you can say, okay, regardless of this delta Q, I want delta V to be only 5 volts. Then you can determine the size of your capacitor. Okay?
If I'm using like solar panels with this topology,
Mm-hmm.
and they want to cascade 2 topologies of these together, is it possible?
You mean replacing these capacitors with solar panels? Theoretically, it's possible. It is not advised, however, because for a variety of reasons. For instance, one reason could be when you have a solar panel, you want to continuously draw current from your solar panel. This is how you minimize your return on investment, okay? If your panel is able to give you 20 amps or certain amount of power, you better use it all the time. But here, some of these capacitors are not engaged sometimes, basically. So depending on what mode you're choosing, sometimes you have, for instance, C2 is only engaged. So if there is a solar panel replacing C2, that means C1 and C3 are the solar panels that are not really used. They are like open. So then you can argue that you are not effectively using your solar panels. But yeah, theoretically you can use them. The other thing is, as we were looking at these states, for instance, there might be a state that this capacitor is actually, wait a minute, actually, I would say not at all, actually, because sometimes you're flipping them. So sometimes you're sending energy to your solar panel, so your solar panel is going to be unhappy unless you place a large capacitor in parallel with your solar panel. So it makes it very complicated. So I would say, generally speaking, no, I wouldn't advise that. Other questions? Okay, so we are not going to go through examples of how these multi-level converters could be used, especially in inverter applications, because more or less you are probably going to see them if it is related to your topic of research. If it is not, don't worry about it. What you may not see is how these multi-level converters could be used in even DC to DC applications. Okay, so let's have a few examples of using these multi-level converters in DC to DC applications. So the main applications are inverters, by the way, but here we are kind of thinking outside the box. Okay. All right. So I'm going to start with the simplest converter possible, which is the buck converter. All right, so if you focus on this voltage from here to here, all right, depending on if the top throw is engaged or the bottom throw is engaged, Vx is either Vn or 0, basically, okay? And as it turns out, your output voltage is the average value of Vx. Which turns out to be D times Vn, I mean the duty cycle, and we ought to have a definition for the duty cycle. Okay. So if you look at Vx, Vx is like a stiff voltage because it's either Vn, which is a stiff voltage, or it's 0, is a stiff voltage. And it's actually variable by time. It's like a square shape kind of a signal. And L and C are used to filter that to give us a DC signal on the output side. Okay. So what I can do is I can actually remove this part and replace it with any multi-level converter that I want. For instance, a Cascaded H-bridge multi-level converter. So let's take a look. So I'm going to have, let's say I have two independent sources. Okay. Something like that. So you can see the right-hand side of the topology is still the same. It's an inductor, like a filter, like a low-pass filter with a capacitor on the output side. I still label this voltage to be Vx. And I mean, to make it a little bit easy, I'm going to label these nodes to be node number 1, 2, 3, and 4. And as you can see, we have two independent sources. You can argue that, so this potentially could be used if, for instance, you have two solar panels, okay? Potentially, it's not the best way of doing things, but it could be used for that. So again, I know that the DC voltage drop under steady state conditions, the DC voltage drop across my inductor is 0. So on average, my output voltage and Vx are the same. So the question is, what is Vx? So Vx is, I'm just writing a large KVL, the voltage of, oh, this is node 5, by the way. So Vx, which is basically voltage of node 5 with respect to node 1, going back to KVL, is voltage of node 5 with respect to 4, plus voltage of node 4 with respect to 3, and 3 with respect to 2, and 2 with respect to 1. 5, 4, 4, 3, 3, 2, 2, 1. That's it. Okay, so I'm just breaking down this. And this would be equivalent to the average of the first component plus the average of the second component of the third component and the last component. Okay? Okay. So the question is, okay, what is the average value of V5 with respect to 4? So let's take a look at that. So for that reason, okay, S3, and by the way, this is switch number 4. Okay, so if switch number 4 is in the top position, and this is the bottom position. So if the switch number 4 is in the top position. Okay, so switch 4 is the name of the whole single pole double throw switch. So if it is in the top position, and let's say we need to define a duty cycle for that, from the beginning of the cycle all the way to D4, which is the duty cycle of this particular switch times period, then V5-4 is VDC2. Okay. So basically V5 is shorted to the top or the top plate of my source. V4 is the negative plate of my source. VDC2 we are talking about, therefore it's VDC2. Otherwise, my bottom throw is engaged, throw number 2, and this is for the remaining of the period. And that means 5 is shorter to 4, therefore the voltage is 0. Okay, so on average, V54 is nothing but D4 times VDC2. Okay, so we took care of this term. Now for the other 3, I can follow the same logic and conclude that, all right, let me see. This turns out to be negative D3 times VDC2. Okay, D3 is the duty cycle associated with switch number 3. Okay, this term turns out to be D2 times VDC1. Okay, and finally the last one is negative D2. I'm sorry, negative D1 times VDC1. All right, so I didn't actually do the logic, I just presenting you the final results. So finally, my output voltage is, remember, the output voltage is the sum of all these terms. There are 2 terms here in which VDC2 appears, and I just factor it out. Okay, so you have something like this. Okay. So this is this is an ideal thing for a quiz, for instance, or even a qualifying exam problem. You know, what is the relationship between your output voltage and all these sources? Okay, so your output voltage is D4 minus D3 times VDC2 plus D2 minus D1 times VDC1. Now, what's interesting is, remember, D4 varies from 0 to 1, D3 the same range, and D2 and D1 are the same. So technically, you can, for instance, presume D3 and D1 are always 0, and you can achieve your output voltage, which could be as high as VDC1 plus VDC2. Or on the other end of the spectrum, you can assume D2 and D4 are always 0, so your output voltage is negative VDC1 minus VDC. So you can actually cover a wide range of output voltage, not only just positive, also even negative output voltages, something like that. So in this very simple case that I had above, I had this one first. So this is a special case of the bottom one. In the bottom one, if I keep D1, D2, and D3 0 and only switch D4, these 2 converters basically act identical. All right? All right, any questions? So we had a paper right away about this. In that paper, what we did was, instead of VDC2, we placed a capacitor. So you have several objectives. One is to regulate the voltage of that capacitor at half of VDC1. So that was one of our objectives. The other objective was, if there is a transient in the system, for instance, all of a sudden your load changes, and Vx, all of a sudden you need a very large value for Vx to push up the inductor current to a higher value or ramp it down very, very quickly. So if a transient, so the system was able to detect a transient in the load by, for instance, measuring the current of the load or measuring the current of the output capacitor. Those ways you can see if there's a sudden change in those currents, that means all of a sudden your load has changed. And in that case, for instance, we could manipulate the system to apply VDC1 for a very short period of time, VDC1 plus VDC2 at Vx. So we have a very large voltage over here, and that very large voltage, for instance, pushes your inductor current to go very high, rapidly very high. And then once the transient was over, then we resume the regular PWM. So this way we were able to actually improve the dynamic response of our converter. So if a typical converter, if the load changes and you see a giant dip in your output voltage, what we were able to see was almost nothing, something like this. So in applications where, for instance, this dip is really important to you not to be there, you can actually do this. However, the catch is you have an extra H-bridge in the system, so more cost, more conduction losses, because these switches have to be on and off anyway, so they are on the path of your electric current. So we had a paper on this one, trying to take advantage of this for the purpose of improving the dynamic response of a buck converter. So this part was the buck, and this was the H-bridge fed by a capacitor to your buck, basically. All right, any questions so far? All right, so let's have another example of using multi-level converters for DC to DC power application, and this time instead of a cascaded H-bridge, I'm going to use a flying capacitor, basically converter. Yes?
Can we generalize this one? Instead of D4, we say M of D. So in case of boost converter, we used 1 minus D4, 1 over
Okay.
1.
Generalize it in a sense that finding a relationship between S3 and S4 so we can factor out D4, you mean?
Yeah, I mean, we can find like general.
So technically here you have 4 independent parameters or numbers of D1, D2, D3, and D4. However, I don't really know how to answer that, because even if you factor things out, you still have all these 4 independent parameters there. So if you want to give one of them up, and for instance say D3 is always 0 or 1, unless you don't want to make that assumption, it should be a parameter there. I don't know how you want to represent it, but it's an independent parameter somewhere in the system, appears in your equations. Questions? Other questions? Yes.
What's the advantage of the second H-bridge? It seems like you could do the same thing with just the first H-bridge.
What do you mean the same thing? If I only use the first H-bridge, I only have this term.
Okay, that's right. I'm sorry. You wouldn't get the extra voltage boost.
Exactly.
Right.
So that's part of it. Yeah. All right, questions? Okay, so let's move on. And by the way, in this analysis, I assume that all of my switches have identical switching periods of T. If they don't have identical switching periods, then it's gonna the voltage transfer ratio would be messier than this is. Okay, this one disappeared here. All right, so let's move on to the next example, and that is using a flying capacitor. So let's have another example. Okay. All right. So I'm gonna keep the number of levels as little, only one flying capacitor, and I'm just gonna use ideal switches. So this is the capacitor, and this is my main source. And this would be V over 2. Okay, something like this. So as long as switch realization is concerned, this would be equal to a MOSFET or an IGBT with the diode, assuming that your output current is bipolar, but this is unipolar. So this is another example. This particular one, if I remember correctly, it is called three-level buck converter. All right. So the switching scheme is basically something like this. The VX that we are trying to synthesize is something like this. So this is, for instance, Vn minus Vc, which turns out, okay, let me write it here, Vc 0. Okay, so we have one, like a standard period. We divide it into two equal halves, and then in the first half, using our switching, let me label these S1, S2. Okay, the most inner one, let's go with S1. Okay. So during the first portion of the first half, we turn basically S2 on, and S1 off. So technically what's happening is this is the loop that the current is flowing through. So your Vx is Vn, which is your source, minus the voltage of the cap, which is Vn over 2. So Vn minus Vn over 2 gives you Vn over 2. Oops. So this gives you Vn minus Vn over 2, which gives you Vn over 2. Then you're applying 0. That means S1 and S2 are both off. So technically we have this as our loop basically. And then for the second half of our switching period, we apply Vc itself. First of all, let me highlight this, that this is Vc. Okay, what does that mean? That means keep S2 on. I'm sorry, S1 on. And S2 off. Okay, in that case, our conduction path would be this. All right, so we are just applying the capacitor to provide power. And since the voltage of the cap is Vn over 2, this also gives us Vn over 2. Okay. So if you, well, we're running out of time. I'm going to start here again. We're going to have like a 5-minute discussion on this and move on to the next application for these kind of converters. this topology has many advantages. That means you can there is an inherent division by 2 in addition to the buck action that is going on. So you have your input to output voltage transfer ratio is D, which is the duty cycle, divided by 2. So this would be good when you have an extreme voltage transfer ratio. For instance, you're trying to convert 48 to maybe 2. A classic buck may not do it, but this would do a better job. All right, so see you guys next week on Tuesday.